Welcome for the next session of computer graphics. Today we will study 2D transformations. The objective is to understand and apply various methods and techniques for 2D transformations. And the outcome is the students will be able to understand and apply core concepts of computer graphics for transformation in 2D dimensions. Let us study 2D rotation. Suppose we are having the point P1 having the coordinates x and y. Then it will be represented in 2D dimension like this, where this length of this line will be L, this is x and this is y. Let us say this is angle theta. So the L will be calculated as square root of x square plus y square, and sine theta can be calculated as opposite side upon hypotenuse, that is x upon L. Y upon L, and cos theta will be calculated as adjacent side upon hypotenuse, that is x upon L. Now if we consider point P1, 0, that is this point, then the length of this line will be 1. So if we calculate cos theta and sin theta, then we can calculate it as our point is 1, 0, and if we multiply it by the matrix A, B, C, D, then we will get another matrix AB. That is cos theta will be A and sin theta will be B. That is sin theta in this case is opposite side upon hypotenuse, that is it will be y upon L, but L is 1, which is already calculated, that is y. So sin theta is equal to y, and cos theta will be calculated as adjacent side upon hypotenuse, that is x upon L, but here L is 1, so x upon 1 equal to x. That is our new point will be x, y after the rotation by angle theta with respect to origin. Similarly, if we consider the point P 0, 1, that is which will be plotted here, then the length of this line is again 1. So if we write a matrix minus sin theta and cos theta, and we multiply by our point 0, 1 by A, B, C, D matrix, then the answer is C and D. That is minus sin theta is C and cos theta is D. That is, we can calculate sin theta as opposite side upon hypotenuse, that is minus x upon L. But L is 1, so the answer is minus x. And hence x is equal to minus sin theta. Also, cos theta is adjacent side upon hypotenuse, that is y upon L, that is y upon 1 equal to y. Thus, we will get the transformation matrix for 2D rotation in the anti-clockwise direction, that is towards this direction. So if theta is the angle in radians, then the transformation matrix for 2D rotation in anticlockwise direction can be written as cos theta sin theta minus sin theta cos theta. Let us see one example. Suppose we want to rotate a point 2, 3 in the counterclockwise direction by an angle pi by 6 radians. Then the point will be represented by a matrix 2, 3, and our rotation matrix for anticlockwise direction is cos pi by 6 sin pi by 6 minus sin pi by 6 cos pi by 6. That is, if we calculate these values, we will get this matrix. And when we multiply this point with this rotation matrix, we will get the point 0.232 and 3.598. That is, when we rotate the point 2, 3 by the angle pi by 6 radians in counterclockwise direction, then the new point will be located as at 0.232 and 3.598. Now, the transformation matrix for 2D rotation in anticlockwise we have already calculated as cos theta sin theta minus sin theta cos theta, where theta is a positive angle. Now, when we want to rotate in clockwise direction, then we use negative angle. That is, replace theta here by minus sin minus theta. So our rotation matrix will be cos minus theta, sin minus theta, minus sin minus theta and cos minus theta. You can simplify this matrix by replacing cos minus theta by cos theta and sin minus theta by minus sin theta. So the rotation matrix for clockwise direction is cos theta minus sin theta, cos theta. For example, again we want to rotate the point 23 by pi by 6 radians but in the clockwise direction, that is in this direction. Then we will write the matrix now like this. So 2 3 point is represented by 1 by 2 matrix like this, and this is the rotation matrix for clockwise direction by pi by 6. If we simplify this, we will get this matrix, and when you multiply these two matrices, we will get the point 3.232, 1.5. Now, let us see 2D translation. If we want to move a point x1, y1, then suppose we want to translate it by factor tx and ty, where tx is the translation towards x-axis and ty is the translation towards y-axis. Then the new point is suppose x2, y2, which will be calculated as x2 is equal to x1 plus tx and y2 is equal to y1 plus ty. For example, our point is having the coordinates 4, 5 and we want to translate along x direction as 3 and along y direction with factor 6, then x2 will be calculated as x1 plus tx, that is 4 plus 3 is equal to 7, and y2 will be calculated as y1 plus ty, that is 5 plus 6, that is 11. So our translated point is 7, 11. Then let us see what are the homogeneous coordinates. Generally, for 2D transformation, we represent the matrices by 2 by 2 size. When we want to represent the point using homogeneous coordinates, then we use 3 by 3 matrix instead of 2 by 2. So we have to use a dummy parameter w. So points are specified by 3 numbers instead of 2. That is, point xy is represented by xw, yw and w. So in general, in 2 dimensions, w value is kept as 1. So scaling using homogeneous coordinates will be represented as follows. So our 2D scaling matrix Sx0, 0, Sy, in homogeneous coordinates it becomes Sx0, 0, 0, Sy, 0, 0, 0, 1. That is, our point xw, yw, w will be multiplied by this matrix, scaling matrix in homogeneous coordinates. We will get a scaled point as x into w into sx, y into w into sy and w. When we divide this by w, then we get correctly scaled point as x into sx and y into sy, which is a point in 2D. Similarly, the counterclockwise rotation matrix in homogeneous coordinates will be represented as follows. So this is our rotation matrix for counterclockwise rotation by angle theta as cos theta sin theta minus sin theta cos theta. In homogeneous coordinates it becomes cos theta sin theta 0 minus sin theta cos theta 0 and 0 0 1. That is our point xw yw w when multiplied by this homogeneous rotation matrix we will get this point. And when this point will be divided by w, then we will get the correctly rotated point as x cos theta minus sin theta as the x coordinate and x sin theta plus y cos theta as the y coordinate. Then similarly, the for translation using homogeneous coordinates, you can use as follows. So this will be the matrix for translation by Tx and Ty using homogeneous coordinates, that is 1 0 0 0 1 0 and Tx Ty 1. That is our point xw yw w when multiplied by this homogeneous translation matrix we will get these points. And when we divide this point by w we will get correctly translated point with x plus tx as the x coordinate and y plus ty as the y coordinate. One example. Suppose we want to magnify the triangle with vertices a00, b11 and c52 to twice its size as well as rotate by 45-degree anticlockwise. Derive the transformation matrices. Now here we are having 3 points A, B and C. So we can represent this triangle having A, B, C coordinates with this matrix of size 3 by 2, where this represents our point A, second row represents our point B and third row represents our point C. Then we want to magnify the triangle to the twice of its size. Means our scaling matrix will be 2 0 0 2. When we multiply this triangle matrix with scaling matrix S, we will get another matrix that is 0 0 2 2 10 4 after the scaling. Then next is rotate the triangle by 45 degrees anticlockwise. So whatever is the scaled matrix obtained, this matrix we will multiply by a rotation matrix cos 45 sin 45 minus sin 45 cos 45. We will get this matrix when we will solve this. Then when this matrix and this rotation matrix are multiplied, we will get this matrix. So after magnification, we will get another point with A 0 0, B 0 2.8 and C will be 4.242 and 9.898. See one more example. Apply translation and scaling transformation to figure A and figure B to get figure C. Now here figure A is having this square and figure B is having the triangle, and we want to apply translation and scaling so that we will get this triangle shifted within this square. To solve this problem, we can have first scaling with Sx 1 by 2 because the width of this triangle base is 2 and we want to shift it so that the base will be 1. That is along the x direction we want to scale it to reduce the size to the half. So that's why here the scaling factor in x direction is 1 by 2 and there is no change in the y direction. Then when we multiply the triangle with this scaling matrix x, we will get this new matrix. Now then we will translate the triangle so that the triangle will be shifted by 1 along this direction, that is y direction. That's why our translation by along the x direction is 1 and translation along the y. This is our translation matrix. And finally when you multiply this matrix by the translation matrix, we will get this matrix.